So now we've seen the microscopic, or the macroscopic, version of the ideal gas law. Let's do a couple examples and see how this thing actually works. So the first example says that we have some sort of container, which say has a piston pushing down, so that it's at exactly half of the volume, which means that the initial volume in this case is equal to 1 liter. We do a measurement. We find the initial temperature is at 20 degrees Celsius. The initial pressure is at 1 times 10 to the 5th pascals. And from here, we want to know what is the number of moles inside of our gas. That's part A. Part B, then, the gas is then going to push on the piston. The piston is going to rise so that the final volume is exactly twice the size of the initial volume. But the pressure we find falls to atmospheric pressure. And we want to know what is the final temperature. So first things first is, now, again, when I talked about this in the initial video, what I said was that whenever we talk about thermodynamics, even in this case, when we're talking about ideal gas law or the thermal physics, what we need to talk about are equilibrium positions. Now, what we know is that initially this thing is at equilibrium, and at the end state it's also at equilibrium. So this thing is at equilibrium twice. Now, since it's at equilibrium, what this means then is we can use the initial scenario to find the number of moles, right? So basically what we know from part A is that using the chemistry version, we have PV is equal to nR times T, but in this case we know this happens at initial pressure, initial volume, and initial temperature. So from here we find is that N then must be equal to the initial pressure times the initial volume divided by the universal gas constant times the initial temperature. Now, things to note here is that these have to be in completely the correct units. So for pressure, we have to have this in pascals, which we're given in pascals. For the volume, this has to be meters cubed. So we have to look up the conversion between a liter to a meter cubed. And then temperature has to be in units of Kelvin, which means that here we have to be a little bit careful because this is an additive change and not a multiplicative change, which means that here, to turn this into Kelvin, we have to add on 273.15. So as long as we put this in the right units, we find in this case then is that this has 0.0616 moles worth of gas. Now for part B, again, what we know is that, again, we have to go from one thermal equilibrium state to a final equilibrium state. So basically what that means then is that even though this ideal gas law is satisfied at the beginning, it also has to be satisfied at the end. So here we also have to have that the final pressure times the final volume must be equal to N times R times the final temperature. Now from here, we have two ways to solve this. So either we can solve this directly for the final temperature, using the fact that we have N from here, but we have to assume that we didn't calculate N wrong. Or what we can notice is what? Since this is true, well, if we take the ratio of these two values, what's going to happen then is that R and N are actually going to vanish, right? Because the number of moles isn't going to change as this thing simply expands, because I have no gas entering or leaving my cylinder. The only thing that's happening is I'm changing the volume of it. That doesn't change actually the number. So in this case, if I take this and I divide by this, again, the N's are going to cancel, the R's are going to cancel. And now I'm going to have this in terms of all known quantities, right? So let's actually do that. So here, if I take the ratio, I get the final pressure times the final volume divided by the initial pressure times the initial volume is then equal to simply the final temperature divided by the initial temperature. So from here, this tells me then that what? The final temperature is simply equal to the initial temperature times then the ratio of the final pressure to the initial pressure times the ratio of the final volume to the initial volume. Now here we know this is what? 1 atmosphere, but we know 1 atmosphere is 1.013 times 10 to the 5th pascals. So here we're going to use that. Here we also know that the final volume is simply twice the initial volume. So this ratio here is actually the same thing as simply 2. So now again, here we have to be careful because we can't use this in Celsius. This has to be in Kelvin, which means that here we can't simply multiply this out using 20 degrees Celsius and get the correct answer. And again, the reason for that is it's an additive change and not a multiplicative change. So since I'm adding instead of multiplying, I'm changing the ratio. So if this was a multiplicative change, what would happen then is that that multiplicative factor would basically just cancel because I'm now just multiplying and dividing. But here now, since I'm adding a term to it, I'm changing the size of that number, which actually changes the ratio then. So anyways, if I plug in my numbers, I get 122.8 degrees Celsius after I've subtracted off that 273.15. So good, so that's our first example. Let's do one more. So the next example says that we're walking on a beach and we find a bottle laying on the beach, which has some note in it. Could be a treasure map, could be a love letter, could be help me, I'm lost at sea. I don't know, something along these lines. And it's inside of the bottle, and the bottle has a cork, right? So basically, what we want to do is get the letter out, maybe the treasure map, we don't know, get it out of the bottle without destroying the map. Now, one way we can do it is we can try to smash the bottle on the ground, but as it breaks, it might destroy the map or the letter or whatever's on the inside, so we don't want to do that. But now that we know about ideal gas law, what we can do is instead heat it up, right? So what we can do is we can take that initial bottle. Let's say here's initially my bottle, which has a cork on the inside, and we can put it over a flame. So here's my flame. So that we heat it up, right? So let's say initially it is 30 degrees outside, so we know that the initial temperature is equal to 30 degrees Celsius. And let's say that the cross-sectional area of the cork is equal to 2.3 centimeters squared. And we're going to put this thing at atmospheric pressure. So we know that the pressure initially on the inside and outside, so P in is equal to P out. So this is initially P in, is equal to 1 atm. So this is equal to atmospheric pressure. So we're going to put this over the flame. In this case, what we find then is that it takes this thing to reach a final temperature equal to 99 degrees Celsius before the cork comes popping out. Okay. So good. So the first thing we want to know then is for part A, what's the final pressure? So once we reach this thing to 99 degrees Celsius, what is the final pressure? And then for part B, what we want to know is what is the static friction equal to right before the cork pops out? So right before that cork pops out, what is the value of the static friction that holds this thing in equilibrium? So let's look at part A first. So again, part A is we know that this thing has to satisfy the ideal gas law initially, and it has to satisfy it at the end. So what we know is that the initial pressure times the initial volume must be equal to nR times the initial temperature. And we also know that the final pressure times the final volume must be equal to nR times the final temperature. Now in this case, we know again that the number of moles on the inside must be the same because the core hasn't popped out. We haven't added gas to it or taken gas out. And here we're going to make the assumption that the final volume is the same thing as the initial volume. Now, technically what's going to happen is under thermal expansion, what will happen is that that final volume will be slightly bigger than the initial volume. But we're going to assume that it's such a small enough change that we can ignore it. Okay? So here, by taking again the ratio of these, we can then say that the final pressure times the final volume divided by the initial pressure times the initial volume must be equal to the final temperature divided by the initial temperature. But again, these two volumes we're going to assume are the same. So from here we get that the final pressure is simply equal to the initial pressure times then the ratio of the two temperatures. Now again, we have to be careful that this has to be in Kelvin and not in Celsius. But if I plug this in, this should work out to be about 1.23 atmospheres. So this should be the final pressure. Or in this case, I can just use the pressure in atmospheres. I don't have to put it in pascals because, again, it's a multiplicative change and not an additive change. Good. Now for part B, we're looking for then what is the friction force keeping this thing inside. So let's look at a free body diagram of a cork. Right? So what's happening then is I still have atmospheric pressure pushing inward from the outside, right? Because this bottle is still in air. So in every direction I have atmospheric pressure pushing. But now I have a new pressure on the inside, which is trying to push this thing out. So I have pressure final of this thing pushing out in this direction. But we also know that this thing wants to pop out this way, so the static friction must be in this direction. Right? Now, technically, this thing has a mass, but that's only going to be in this direction, so we're not going to worry about that. And we don't know if the static friction is maximum or whatever. All we know is that it's some sort of static friction. So in that case, we're just going to label it static friction and not worry about the mass. So good. So here, let's take this as our x direction. So we can then say that some of the forces in the x direction are equal to 0, because it hasn't popped out yet. It's still in static equilibrium. Now here, remember, we don't really care about the pressures, we care about the force. So what I care about is that this is a final force, this is an atmospheric force, which are pushing in these directions. So from here, we're going to say then that's what? The final force minus the atmospheric force minus the static friction must all then be equal to 0. So from here, we get the static friction then is equal to the final force minus the atmospheric force. But we know that what? Force is the same thing as pressure times area. So it's going to be the same thing then as what? The final pressure minus the atmospheric pressure, all 10 times that cross-sectional area. Because we're assuming this has uniform cross-sectional area, so the area here is exactly equal to the area here. Now again, here the area has to be in meters cubed, so we have to make sure we put this in meters cubed. Here this has to be in pascals and not atmospheres. But anyways, if we plug in our numbers, what we find is that this should be about 5.24 times 10 to the minus 5 newtons. Good. So these are two examples of using the macroscopic version of ideal gas law. Again, this is the states of the gas inside of some sort of container, looking at what we can actually measure from the outside, not being inside of the gas itself. And again, all we can measure is the pressure, the volume, and the temperature. But again, these things hold in the ideal gas law, but again, only in thermal equilibrium. Meaning as this thing is increasing its temperature from the initial temperature to the final temperature, this ideal gas law does not hold anymore. It is outside of equilibrium, unless it's doing it in a quasi-static type of way, so meaning the temperature is increasing very slowly, so it's always basically in equilibrium. In that case, then you can say that, but typically all we can say is that this is only true when it's in equilibrium, which is typically going to be our final and our initial.